SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today we shall discuss about the limitations of Carnot cycle, and then we shall go to discuss about the actual cycle starting with the simple Rankine cycle. You know that in the last class we have discussed about the ideal vapor power cycle, that is the Carnot cycle. We have also tried to estimate the heat which is added to the cycle and the work which is extracted from the cycle, during different processes. So, if we try to just draw the schematic of the simple power plant, why I am telling simple. So, this is I am writing compressor, and so this is W out, Q out, this is Q in, and this is W in. We have discussed about the TS diagram, and if we use another color to represent, so this is 1, this is 2, this is 3, this is 4. So, this is T 2 comma 3, this is T 1 comma 4. You know that is what we have discussed in the last class, and this hatched portion, the W net. Okay. And if I use another color, so this is the area representing the heat rejection. Of course, I should write in the specific form. So, this is Q out, so this is S. I am not going to discuss again. So, basically 1 to 2, that is the process, compression process, and we have discussed that this process can be represented by a reversible adiabatic process. So, that is, this is not a device in which heat exchange takes place between system and surroundings, rather it is a work interacting device. In particular, this is a work absorbing device. So, this is process is reversible adiabatic process. We know that reversible adiabatic process, that is, if we write T ds equal to d cube. So, for the reversible adiabatic process, this is equal to 0. So, you know that ds equal to 0. So, if we integrate 1 to 2, that means S 2 equal to S 1, S 2 minus S 1 equal to 0 and S 2 equal to S 1. So, you know that entropy is remaining constant. So, basically isentropic process. So, 1 to 2, that S 2 equal to S 1. 2 to 3 is constant temperature heat addition, reversible isothermal process, and 3 to 4 is reversible adiabatic expansion, that is, the process takes place while steam is passing through the turbine, and finally 4 to 1 is constant temperature heat rejection. So, we could write that this W in is equal to minus H 2 minus H 1, that you can write by using first law of thermodynamics applied to flow processes. Q in, that is heat addition to this device, that is boiler, that is H 3 minus H 2. I am writing in the specific form, and W out equal to H 3 minus H 4 and Q out minus H 4 minus H 1, right. So, all these 4 quantities we have discussed, these you can write it by applying first law of thermodynamics applied to steady state steady flow processes. Here this negative sign indicates that work is added to the system, and in this expression the negative sign indicates that heat is rejected from the system. So, this is the sign convention we have talked about in one of the previous classes, that in thermodynamics you can follow a particular sign convention. So, if you consider normally what is followed, heat added to the system is taken as positive and work taken out or taken away from the system is taken as positive. So, work which is coming out from the system should be taken as positive. Considering this sign convention, this is the work which is added to the system. So, that is why it is negative. Heat which is added to the system is taken as positive. Considering the sign convention, this is the amount of heat which is being rejected from the system from the cycle, that is why it is known as, that is why it is negative. So, what about the efficiency, thermal efficiency? Thermal efficiency will be eta thermal W net by Q in, right. So, we can write what is W net, W out minus W in. So, if we try to look at what is W t, so W net is H 3 minus H 4 minus H2 minus H1 divided by Q in is H3 minus H2. So, you can clearly see that by doing some algebraic manipulation H3 minus H2 minus H4 minus H1. So, what we can do? We can simply write it W in H2 minus H1. So, what we can write? We can write one step further, that is H3 minus H2 divided by H3 minus H2 minus H4 minus H1 divided by H3 minus H2. So, basically if we go to the next slide, we can write thermal efficiency equal to 1 minus H4 minus H1 divided by H3 minus H2. See what is H4 minus H1, that is Q out. So, this is Q out. Negative sign is used to indicate that it is the amount of heat which is rejected from the system. Okay. So, we can write this is nothing but 1 minus Q out divided by Q in. See, in the last class we have discussed that the Carnot cycle comprising of two reversible adiabatic processes and two reversible isothermal processes. For the reversible cases, we can write it 1 minus Q out minus Q in. So, basically you know that the heat rejected at a temperature which is T4 or T1 and which is added at a constant temperature, that is T2 and T3. So, we can write it Q out, that is 1 minus T4 by T1 by T2. So, this is T2. T4 by T3 or 2. So, this is we can write for the reversible processes that you have studied in thermodynamics. So, we can write it 1 minus that is T lower divided by T higher. So, this is the low temperature of the cycle and this is the high temperature of the cycle. So, try to understand, even though it is an ideal cycle, what we can understand from this expression is that if we reduce the low temperature part of the cycle, then efficiency can be increased. Contrarily, if we increase the high temperature side, high temperature part of the cycle, then that efficiency will increase. So, there are two ways by how the efficiency or thermal efficiency of the Carnot cycle can be increased. So, this is Carnot. Okay. Either by reducing the temperature of the lower part or low temperature part of the cycle, or by increasing the temperature of the high temperature part of the cycle, we can increase the efficiency of this cycle. So, you know that if you would like to reduce the low temperature part of the cycle, that means we need to reduce T4 and T1. So, problem is if you would like to reduce the temperature of T4 and T1, that is that can be done again, but by doing this we are also going to invite another problem that we shall discuss in one of our subsequent classes. On the other hand, if we try to increase the temperature of the high temperature part of the cycle, so basically try to understand this part, this condenser part is basically this is the low temperature thermal reservoir. So, if we reduce the temperature of the low temperature thermal reservoir, we can increase the efficiency of the cycle. This is the high temperature part of the cycle, that is that is the high temperature thermal reservoir. So, if we increase the temperature of this reservoir, we also can increase the efficiency of the cycle. So, if you would like to increase the high temperature part or temperature of the high temperature part of the cycle, that is the temperature of high temperature thermal reservoir, we need to have some more input energy, that is the fuel that is used to supply heat to the boiler. So, again it is not economical point of view. On the contrary, if you would like to reduce the temperature of the lower temperature part of the cycle, we are also going to invite one problem related to the condenser pressure, that we will discuss later. So, this is basically what is done. Now, this is basically, though we know that this is the ideal cycle, then I mean why do we need to study this particular cycle? So, this is essentially a cycle which is used to compare the performance of all the actual cycles, and that is why this is important. Not only this, if we consider that this cycle, we look at that there are several issues which are not very easy to achieve in practice, which are not easily attainable in practice. Which are those? What we can understand, that process 421. So, let us now discuss about a few critical issues, a few limitations, a few drawbacks. Those are not easy to attain in practice, but knowing fully that those are not easily attainable in practice, we study this particular cycle. Again I am telling only to compare the performance of the actual cycles. So, if we try to discuss about the drawbacks, or limitation of the Carnot cycle. What are those? Number one, if we start our discussion from this particular process, that is 421, or say we start our discussion from process 1 to 2. Which is this process? This is compression process. You know that compression process starts from state point 1 and the process ends at point 2. So, the process starts at point 1, which is the two phase mixture. So, basically the compressor needs to handle two phase mixture corresponding to this state point 1, I mean the quality of this two phase mixture. So, since the compressor needs to handle two phase mixture, we all know the specific volume of vapor is higher than the specific volume of liquid. So, handling two phase mixture will be required higher power consumption. So, W in that should be supplied to run the compressor will be very high, accounting for the higher specific volume of the vapor corresponding to state point 1. So, this is number 1. So, basically I am writing higher power consumption at the compressor because of handling two phase mixture. Number 2, so this is number 1 drawback. Number 2 is, see, it is very difficult to design a compressor which will start from this two phase mixture and the process will end at state point 2. The process will end at state point 2. So, basically starting with two phase mixture and terminating this process at the saturated liquid line is not so easy. So, design of a compressor which will take two phase mixture as the intake fluid and eventually at the exit of the compressor we will be getting saturated liquid. So, design of compressor is also another issue. So, I am writing design of the compressor which will discharge saturated liquid by taking two phase mixture at the inlet. At its inlet. Number 3, so these two are the two different drawbacks we have identified. What is number 3? Number 3, now you look at the process 4-2, 3-4 and 4-1. If we look at process 4-1, you know that the condensation process starts at point 4. So, the exit stream quality is at 4, the exit stream is also not the just saturated stream at that particular temperature, rather it is the two phase mixture, but the condensation process will terminate at state point 1. So, the condensation process starts at point 4, which is again the state point of the working substance is two phase mixture, and also the condensation process will terminate at point 1, which is also not the saturated liquid. So, this is also not very easy. So, partial condensation. I am writing. So, the condensation up to the state point 1, which is not even the saturated liquid, but it is a mixture having liquid as well as vapor. So, this is partial condensation. So, designing a condenser which will terminate the process at state point 1. So, that is it is not complete condensation, rather partial condensation. Number 4, which we can see, that here we have shown this state point 2 and state point 3 on the saturated liquid line and saturated vapor line. So, this is saturated vapor line and this is saturated liquid line, right. This is saturated liquid line SLL, this is saturated vapor line SVL. So, the point 2 is on the saturated liquid line, point 3 is on the saturated vapor line. For the sake of generality, these 2 points could be shown to be inside the vapor dome. However, we have shown these 2 points to be on the saturated liquid line and saturated vapor line. Now, if we start the expansion process from point 3 and the expansion process terminates at point 4. So, basically that the quality of stream at the exit of the turbine is far away from the saturated vapor line. So, the point 4 which is far away from the saturated vapor line, and had it been a case that the state point 4 is closer to the saturated vapor line, then quality of stream leaving the turbine could be closer to 1. But since the state point 4 is away from the saturated vapor line, so the quality of stream at the exit of the turbine is not very good. So, it is poor rather. So, poor quality of steam at the exit of the turbine may leads to turbine pitting and erosion. So, the poor quality of steam at the exit of the turbine following if we allow the steam power plant to run using this Carnot vapor cycle, then quality of the steam at the exit of the turbine is very poor and it will lead to the turbine blade and pitting problem. So, poor quality of steam at the turbine exit, and it may lead to turbine blade pitting and erosion. Okay. So, we have listed down several drawbacks associated with this Carnot vapor cycle. Considering all these drawbacks, so not only that all process should be reversible process in practice, it is easy to attain all the processes to be reversible one. We have seen that there are a few issues, that is the higher power consumption, design of the compressor which will take two phase mixture at its inlet and terminate, or the process will end at the state point which is saturated liquid, partial condensation, the condensation process will end at state point 1 which is again a two phase mixture, and the quality of the steam at the exit of the turbine is also very poor. Considering all these drawbacks, the concept or the actual power cycles came into the picture. Again I am telling, we have discussed about the Carnot cycle, that is the ideal vapor cycle. We have seen that to complete this cycle, we have considered all processes are to be reversible processes. Even if we consider that processes will be reversible process, we have identified 4 different drawbacks from the practical point of view. Now, considering all these issues, the actual power cycle came into the picture, and the first actual cycle, that is Rankine cycle. So, this cycle was initially conceptually developed by a Scottish mechanical engineer William John Rankine. So, to honor the name of this Scottish engineer, this cycle is known as Rankine cycle. Question is, if we now look at the TS diagram of this cycle, we can see that quality of steam at point 4 is very poor. Not only that, I mean, if we try to circumvent the drawbacks associated with the Carnot cycle, that is, if we can if we can extend the condensation process up to the saturated liquid line, then perhaps the design of a condenser which will terminate or allow to have partial condensation can be eliminated. So, the complicated design of the condenser which will allow to have partial condensation can be eliminated. if we can allow condensation process to be terminated up to the saturated liquid line, then instead of using a compressor we can use a pump, because pump cannot handle two phase mixture. So, if we can have this condensation process up to the saturated liquid line, so instead of having two phase mixture at state point 1, we can have only saturated liquid at state point 1 if we can extend the condensation process up to the saturated liquid line. So, it is not a partial condensation. So, the problem associated with partial condensation can be eliminated. Also, if we have at the end of the condensation the state is on the saturated liquid line, we also can use pump. If we can use pump, then we can eliminate these two drawbacks, that is power consumption will be less because pump will handle only liquid, and it is not, again the problem will not be there with the design of the compressor, which will take saturated liquid as the inlet and the process will terminate at the saturated liquid. So, basically we can remove all these problems. Remaining problem is 4. So, we can, if we remove the problem associated with partial condensation, we also can remove the problems which we have listed down at point 1 at point 2. So, these are interrelated. For the problem we have written over here, that is poor quality of steam. If we go back, so you know that can we allow the boiling process to be further extended beyond the superheat saturated vapor line. So, if steam at the exit of the boiler can be superheated beyond this point 3, then perhaps if we allow steam to expand inside the turbine following this reversible adiabatic process, then the point 4. So, idea is if we allow, so the possibility of superheating steam beyond point 3, if we do like this, then we can have, so this is 4 prime. So, superheating the steam beyond point 3 would be another way out to increase the quality of steam at the exit of the turbine, which we can see from the schematic, from this TS diagram, that if we extend, rather if we superheat steam from point 3 to 3 prime, we can see at the exit of the turbine the state will be 4 prime and this is very close to the saturated vapor line. So, in a way we are increasing the quality of the steam. So, all these remedies that we have discussed now can be accommodated, I mean in this in an actual cycle. In fact, the Scottish engineer William John McEwan Rankine, who considered all these drawbacks and introduced this actual cycle, that is Rankine cycle, in which all these drawbacks can be eliminated. So, let us first discuss about the Rankine cycle. I will be discussing about the TS diagram. So, this is TS diagram. So, you know that this is so, this is the TS diagram. So, let us now discuss one by one. You can see that point 1 is on the saturated liquid line. So, if we use, so this is saturated liquid line and this line is saturated vapor line. So, point 1 is on the saturated liquid line. So, the condensation process is not now the partial condensation. So, condensation process is getting terminated up to the saturated liquid state. So, now instead of using compressor we can use pump. So, if we try to draw the schematic again, so this is boiler, so this is the turbine. Now, this is pump, so this is 1, this is 2, this is 3, this is 4. Q in, so this is turbine. W in. So, instead of using compressor we can use now pump. Since pump cannot handle two phase mixtures, the consumption of power will be less because it is used to handle only liquid. So, you can see, so it will be pumped to up to state point 2 and then 2 to 3, that is the heating inside the boiler at constant pressure. So, instead of having constant temperature heating, which we have seen from this TS diagram, which is for the Carnot vapor cycle, now we are having heating, but it is not at the constant temperature, rather at the constant pressure. So, this is the constant pressure line on the TS diagram. And finally, we are having expansion of the steam inside the turbine 3 to 4. Now, see what I was discussing, that if the process would have been like this, that the heating process ends at 3 prime, then if we allow steam to expand from 3 prime, you can see from this TS diagram that the quality of steam at the exit of the turbine will corresponds to the state point 4, quality state of state point 4. Since the point 4 prime is away from the saturated vapor line, because quality of this particular state is x equal to 1. So, the point 4 prime is away from x equal to 1 line. So, the quality will be very poor, but by superheating steam beyond state point 3 prime up to point 3, we can see that the quality of steam at the exit of this turbine is improving. So, quality is better. Now, this is the TS diagram. So, you can understand that the problems or drawbacks associated with the Carnot cycle now can be eliminated by using this Rankine cycle. This cycle is known as simple Rankine cycle. Still we can call it simple ideal Rankine cycle, because we are assuming that the process are reversible process. So, this is reversible adiabatic process, that is pumping. Then this is constant pressure heat addition, we are again considering the process is reversible process, and you can understand from the process 3 to 4 which is there in the turbine is again reversible adiabatic expansion, because entropy at 3 is equal to entropy at point 4. In actual practice, process will not be like this, some degree of irreversibility will be there. And finally, the heat rejection is again not a constant temperature, rather it is constant pressure heat rejection, that is this point. So, this is, so this pressure P3 equal to P2 equal to P boiler, and this pressure, that is P4 equal to P1, that equal to P condenser. Okay. So, constant pressure heat rejection. Now, question is, two things I would like to discuss. First of all, if we try to draw the PV diagram, This is very important. So, this is what is the, so this is state point 4, this is 3, okay, prime, this is 1, this is 2. Now, question is, if we even do not go for superheating steam beyond 3 prime, this is also the simple Rankine cycle. So, whenever I am talking about simple Rankine cycle, so I am writing simple Rankine cycle, that is 1, 2, 2 prime, 3, 4. So, this is the simple Rankine cycle, and at least we have eliminated the problem of designing a compressor which will take two phase mixture as the inlet at the inlet, and at the outlet it will be saturated liquid. And also, if we are not using compressor, because the quality at state point 1 is that is only liquid, saturated liquid. So, the power consumptions or high power consumption is not there, because pump only handling saturated liquid. So, as I told you that handling two phase mixture needs higher power consumption, because specific volume of vapor is higher than the specific volume of the liquid at any given pressure. So, at any given temperature or pressure. So, that here we have drawn the PV diagram of the simple Rankine cycle, that is 1, 2, 2 prime, 3 and 4. So, now provision is there using the cycle that we can increase the we can superheat steam even beyond 3 prime up to 3, essentially to increase the quality of steam at the exit of the turbine. So, simple Rankine cycle, we can see that we can heat up to the saturated vapor line, then we can allow steam to expand isentropically. So, this is the PV diagram for the simple Rankine cycle. Okay. So, this is what we can see, and also we can draw the HS diagram. So, if I try to draw the HS diagram, this is also very important diagram, because that so this is the this is 1, this is 2, this is 3, this is 4, right. Okay. So, this is the HS diagram. Now, I can write this is P condenser and this is P boiler. Okay. So, this is X4, this line. The beauty of this diagram, you also can get the quality from the same diagram. I am not going to discuss this particular issue. So, this is what is the simple Rankine cycle. Idea is we can eliminate the problem associated with the ideal Carnot cycle. If we can eliminate, the cycle becomes more practical. So, the processes which are there in real practice can be compared by using the processes which we have mapped in TS plane, but all these processes correspond to Rankine cycle. So, all these processes constitute together to form a cycle which is known as the Rankine cycle. Okay. So, again what we need to do, we need to go for the mathematical quantification of the efficiency. So, you can understand that heat basically process 1 to 2, that is process 1 to 2, that is reversible adiabatic pumping. So, this is W in equal to minus V dP from 1 to 2, right. So, that is we have discussed about this process minus V dP. So, you can try to understand what is so basically it should be minus V F at 1 P 2 minus P 1. So, this is boiler pressure minus condenser pressure. Now, process 2 to 3, that is constant pressure heat addition. So, it is not the heat addition at constant temperature, rather it is constant pressure heat addition. So, cube, that is H 3 minus H 2. I am writing this heat addition, that is a specific heat which is added, H 3 minus H 2, and process 3 to 4, that is reversible adiabatic expansion, and W out equal to H 3 minus H 4, right. So, this is reversible adiabatic expansion H 3 minus H 4 or H 3 prime. So, I am writing 3 and 3 prime because I should write this is 3 prime, not 3, and finally, the process is 4 to 1 constant pressure heat rejection. So, this is Q 4 1, that is H 4 minus H 1. So, negative. So, because it is the amount of heat which is rejected from the system. So, now you can understand. So, this is the amount of heat which is rejected. So, this is QL. So, this is QL heat rejected, this is Q out, this is QH. So, this is QH. So, this is heat supplied, right. So, what we can do, we can quickly calculate what would be the efficiency. So, thermal efficiency of the Rankine cycle should be again W net by Q in. So, this is the thermal efficiency of the Rankine cycle, that is W net by Q in. So, what we can write? So, let me tell you again, this is basically work done, this is specific volume of the liquid corresponding to state point 1. So, if we know the pressure at or condenser pressure, at that pressure the volume of the saturated liquid, and what if we know the pressure of the boiler pressure, rather the pressure at which boiler is operating and the pressure at which the condenser is operating, we can calculate what is W in. So, this is basically the constant pressure heat addition. So, H 3 minus H 2 that we are getting from first law, again we are getting from first law applied to steady state steady flow processes. I have discussed this part. So, this is reversible adiabatic expansion, this is also you can get it from the first law applied to steady state steady flow processes. So, and finally, this is the heat rejection. So, now this is the amount of heat which is rejected if you have visited any thermal power plant, you will find that this is the amount of heat rejected in cooling tower. So, heat rejected to cooling water, okay. And this is the heat supplied by burning fuel. So, this is the amount of heat which is supplied to the system by burning fuel, and this is the amount of heat is rejected to the cooling water which is supplied in a closed circuit through the cooling tower. So, this is W net by Q in. So, eta thermal Rankine, so equal to W net by Q in. So, we can see what is W net, that is H 3 prime minus H 4 prime. So, this is minus, this is what is W pump, that is. So, this quantity basically H 2 minus H 1, change in enthalpy, right. So, you know that basically we can write H 2 minus H 1 divided by Q in. So, that is the Q in. So, heat added, heat supplied H 3 minus H 2. So, H 3 minus H 2. So, it should be again H 3 prime, because I am using H 3 prime. So, 3 prime, because I am assuming that the 1, 2, 2 prime, 3 prime, 4 prime is the simple Rankine cycle without superheating. So, there is no modification, just simple ideal Rankine cycle. So, this is the amount of heat added following this line 2 to 3. Okay. So, this is the case. So, if we write, we can write it H 3 prime minus H 2 minus H 4 minus H 1 divided by H 3 prime minus H 2. So, it will be 1 minus H 4 minus H 1 divided by H 3 prime minus H 2. So, this is the expression of the efficiency of this, the thermal efficiency of the Rankine cycle. You can understand that here this VDP, that is nothing but change in enthalpy of the liquid because of this pumping process. So, this quantity again can be compared with the efficiency that we have following the Carnot vapor cycle, and if we compare, we will find that the efficiency of the ideal simple Rankine cycle is less than the efficiency of the ideal Carnot cycle. Let me tell you again, if we compare this quantity with that which we have obtained, that means the efficiency of the Carnot cycle, efficiency of the Rankine cycle, thermal efficiency of the Rankine cycle is compared with the thermal efficiency of the Carnot cycle, we will find that the efficiency of the simple Rankine cycle is less than the efficiency of the simple efficiency of the ideal Carnot cycle. Reason is quite obvious, because you know that if we look at this particular diagram, the heat is added not at constant temperature, which was the case for the Carnot cycle, but in this case the heat is added at constant pressure. So, there are two sub parts, one is 2 to 2 prime and next is 2 prime to 3 prime. So, this heat addition has two parts, one is 2 to 2 prime and then 2 prime to 3. So, this is 2 prime to 3 prime, 2 to 2 prime, that is sensible heat transfer, and 2 prime to 3 prime, that is phase change or the latent heat transfer. So, you know that this sector, this particular section, that is 2 to 2 prime, that is the sensible heat transfer, you can see that the temperature increases. So, liquid temperature increases from T2 to T2 prime, and then again heat is continuously added, but there is a phase change, and we can see that this is the heat transfer, that is latent heat transfer. So, it is because of this particular section, average temperature of heat addition reduces. So, the average temperature at which heat is added to the boiler for this particular case, that is following this Rankine cycle, is less than the heat which is the temperature at which heat is added in the Carnot cycle. So, this particular sector, say if you consider this is the Rankine cycle, if we consider this is the Rankine cycle. So, if we consider 1 prime, 2 prime, 3 prime and 4 prime is the Rankine cycle, that is what we have seen in the previous slide, but now the problem associated with the partial condensation has not been there, and we are having the liquid at point 1, that is saturated liquid. So, we are pumping, and now earlier it was compressed from 1 prime to 2 prime and then constant temperature heat addition, but it is now pumped to 1 prime to 2 up to the boiler pressure, and then 2 to 2 prime, that small segment is there, and where the heat transfer, that the sensible heat transfer takes place, and it is because of this part. So, this part lowers the mean temperature at which it is added to the boiler, and it is because of this reason the efficiency of the simple ideal Rankine cycle is less than the efficiency of the Carnot cycle. We will see mathematically that the simple efficiency of the simple ideal Rankine cycle is less than the efficiency of the Carnot cycle, and this part we will take up in the next class. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.